Hello everyone. So far we have been discussing the fundamentals of nuclear chemistry, all the related topics related to radioactivity, nuclear structure, nuclear models, nuclear reaction, detection and measurement of different types of radiations, and also producing different isotopes. Now, the remaining part of this course, the remaining the 5 lectures or 10 modules of my portion, I will be focusing on the applications of whatever knowledge we have gained in different branches of science, of course, in chemistry as well as other areas. So, before that, I will just like to discuss the basic practices in a radiochemical experiment. So, we do radiochemical separations. We do radiochemical analysis. What are the practices that we need to follow that we will try to discuss in this particular lecture? Okay, so one of the important radiochemical practice is to do separation. Separation of radioactive isotopes we'll call as radiochemical separations. Now, we can have different radioisotopes, or even in the case of actinides, all the isotopes are radioactive. So we can also call them as radioactive elements. So we may be separating actinides, or we may be separating other elements, but using their radio tracers. Now, one of the important advantage of radiochemical separation vis-a-vis the other methods of physical methods, like in physical methods, we can be using detectors. I explained the other day delta EE telescopes, wherein you can separate proton, neutron, alpha particles, and so on. The moment you go to heavier elements, there is a overlapping of the signal due to different elements Z and A. And so in physical experiments, you will find it is difficult to resolve the different Z and A of the products that are formed in a nuclear reaction or even fission. In radiochemical separation, since we are separating the elements radiochemically and then identifying the mass number by following their decay characteristics like half-life or gamma energy, so the resolution means in terms of neighboring elements is unique. We can unambiguously assign the Z and A atomic number and mass number to the particular radioisotope produced in a nuclear reaction. That is what I mean by unique resolution in Z and A. Now, what is the need for this radiochemical separation? Where do we come across? So that is what, let me just give you the brief introduction. Need for radiochemical separation. So, one is to have the requirement of pure radiochemicals. As we go along, we will see that there are many areas, like particularly, when you want to use a radioisotope in medicine, particularly in diagnosis, you require a pure radiochemical, a particular tracer, particularly technetium-99M, bound to an organic molecule, and that formulation should not contain any other chemical form. So that is what we mean by pure radiochemicals for applications. Sometimes even in research, you are synthesizing some particular compound, a labeled compound, and you like to have this as pure as possible. Then we use radio tracers in many areas like industry, healthcare, agriculture, environmental research, and so on. And the requirement, of course, in most of the cases will be we require the radiochemically pure, and also this is called radionuclidically pure, means only that isotopes will be present. Other isotopes should not be present. They may interfere in the experiments. So for producing these pure radioisotopes, we require radiochemical separations. Then we have the important area of short-lived radioisotopes. Many elements, the heavy elements, transactinides, whatever the discoveries are happening at the moment in the area of heavy elements, transactinide, half-lives are all in seconds, milliseconds, and microseconds. So you require very nice radiochemical separation, in fact, the very fast radiochemical separations, so that you can identify the Z and A of these isotopes. So again, that same thing I have mentioned also, chemistry of heavy elements. If you are studying the chemistry of heavy elements, from the time of nuclear reactions, their production and separation involves very fast radiochemical separation. The short-lived isotopes are also many applications in there, like for example in PET, positron emission tomography, to produce F18 or carbon 11 or oxygen 15. They are very short-lived, some of them even seconds. And for the positron emission tomography study, diagnostic applications, you require, after they are produced, require them to be sent to the hospital as early as possible. So they require the fast radiochemical separation. So radiochemical separations have evolved a lot over the last many years, and I'll just try to give you a glimpse of that evolution. So before we go to the different types of radiochemical separations and the applications, let me try to give you the basic principles. The basic principles that we follow in any radiochemical separation. So whenever we are doing radiochemistry experiments, we need to take care of certain aspects and certain terminologies we use, so that you know what is that purpose of the particular type. For example, we say carriers. So in radiochemistry, radiochemical experiments, carrier actually is the stable isotopes of the element of the radioisotope. So we are using a radioisotope as a tracer for radiochemical separations. So to want to trace the path of a radioisotope, a radio element, or you produce a radioisotope in a chemical reaction, maybe fission or a reaction, and you have very few atoms of that particular radioisotope. So if you want to do separation, probably you need to carry that few atoms with a bulk material. So that bulk material made of the same element but different isotope stable ones we call as the carrier. And this carrier in fact are meant to minimize the loss. If you have, let us say, 1 million atoms of an isotope like iodine 131 you produce by tellurium, suppose you have tellurium 130, tellurium 131, tellurium, okay, 130, 131 tellurium, and this is mixed beta minus 2, 131 iodine. I discussed the other day in the radioisotope production. Now this iodine 131 is carrier free. That means only 131 iodine isotopes are there. So if you have a Curie of 131 iodine, you may have about billions or maybe 10 billion, 10 11 atoms of iodine 131. So when you do separation in terms of the amount, 131 gram will contain Avogadro number. So 10 atoms will contain only picogram of quantity. So you cannot handle such a small quantity. In fact, when you put them in a container, many of them will get absorbed onto the wall of the container. So minimize the loss due to adsorption or other, in the reagents. It's better that we use bulk potassium iodide. So you use iodine 127 to carry this 131 iodine. So the losses will be minimized. Many times we require them in a high specific activity. So you don't add a bulk quantity, you add macrogram quantity. 10 power 20 atoms or 18 atoms. Like that, we try because of the Bass effect. So you generate large quantity, not that large, but relatively large to avoid the loss during radiochemical separation. Then there is a term called holdback carriers. So suppose along with the tellurium, you have other isotopes. For example, in fission, you have 131 iodine, you have 132 tellurium. They are fission products. Now, both of them are carrier free, means only atoms of these radioactive isotopes are present. And we want to separate 131 iodine as a fission product, but we don't want to separate 132 tellurium. So for iodine, we may use Ki as a carrier, but to prevent some portion of tellurium going into along with the 131, suppose you do precipitation. silver iodide, then there is a possibility that 132 tellurium may get adsorbed onto the precipitate. So to prevent that adsorption, or you may do solvent extraction of iodine in carbon tetrachloride to prevent the carry forward of tellurium in that extraction, we use some stable tellurium, telluric acid we can use, so that these isotopes of tellurium which are radioactive, they also remain in the raffinate. So that is one way of, so these are hold back, they hold the radioisotope in the place where we don't want them to carry along with the separation. And the third type of reagents are called scavengers, to precipitate unwanted elements before we separate the desired element. So we use these scavengers, are the reagents to precipitate the elements which are not required to be carried forward along with the, like for example, you want to separate barium as barium sulfate or barium nitrate, but along with barium, many rare earths may also go, zirconium may go. So how to prevent that they don't go along with barium? You can do a ferric hydroxide precipitation. So you add ferric nitrate or ferric chloride and ammonia to precipitate all the rare earths and zirconium as hydroxides. And so now whatever is the raffinate, you add barium, the reagent sulfate or nitrate, and you can separate barium in this form. So these are called scavenger. They scavenge the undesired elements from separation along with the desired element. So these are mostly required for precipitation or solvent extraction or even ion exchange separation. Now, one of the important parameters for the radiochemical separation is the half-life. Half-life is very important because sometimes the half-life may be short and your time of separation may be long. So you may lose the whole radioactive isotope. Before it is decaying, you have to separate. Radiochemical purity is, as the name itself mentioned, that what is the form in which a particular isotope is present in the chemical form. That is called the radiochemical. And the purity of that radiochemical. So not only the isotope, but the chemical form. So if you are present for, you want iodine as iodide, you want iodine in presence of, as in the form of iodide, not as iodate. So iodine present as I- is the radiochemically pure form desired, and iodate is a different radiochemical form which is undesired. So you would have to produce iodine 131 as I-, not IO3- in a particular application. When you need IO3-, then you require pure IO3-, I- will be impurity. Radionuclide purity, as the name suggests, 1/3, like molybdenum-99 is a radionuclide, and you want to separate this one. But any other radionuclide, any other isotope of even molybdenum will be taken as an impurity, like molybdenum-93, molybdenum-101. So they are, presence of them in the molybdenum-99 fraction will call radionuclide impurity. So when you say radionuclide purity, is the fraction of only molybdenum-99 in the total molybdenum present in that particular consignment. Also, the specific activity is an important parameter. You require high specific activity in some applications that you define in terms of activity per unit mass, becquerel per gram or curie per gram. So you, depending upon the application, you may have to go for high specific activity or it may not be required at times. And lastly, the radiochemical yield. Many a times you are doing radiochemical separation. What fraction of that isotope has got separated in your final fraction? So you started with, let us say, 10 curie of that particular activity, and at the end you get 9 curie of present in that chemical form. So you can say radiochemical yield is 90%. So this is required to be known. And for that, sometimes radiotesters are also used. In radiochemical separations, radiotesters help in finding out the radiochemical yield. So you can add a radioisotope which is not present in your sample, and finally you see what percentage of this activity has been separated. That will give you the yield of radiochemical separation. So radiochemical separations involve, there are most of the elements you will find there will be a requirement to do radiochemical separation at some point or other. So, for example, you are producing iron, cobalt, you radiate some targets of iron, cobalt, nickel, and produce some isotopes of them. And you may suppose you have an alloy and you want to separate a particular isotope. You need to do radiochemical separations. You may require to, like actinides, you want to separate from each other, or lanthanide you want to separate each other. The classic example of radiochemical separation, when you have a large number of radioisotopes present together, is fission products. You irradiate uranium with neutrons, you get hundreds of fission products. The half-life ranging from seconds to years. So you have the fission product starting from, let us say, selenium. Yield of selenium may be 0.01% or so. And the yield is going up, it's reaching maximum around molybdenum. And then it is again goes minimum around cadmium tin, cadmium indium tin, 0.01%. Goes up, it becomes maximum around cesium barium, and then finally goes down again with the rare earths. So all these fission products, and now of course we have the high resolution gamma spectrometry setup. So you can directly see the gamma rays of the fission products. So a large number of fission products you can see together in a gamma spectrum. But earlier, when we didn't have the high resolution gamma spectrometers, we used to do the chemistry of each element. So much so that we remember the chemistry of each element, how to separate. For example, you do iodine, immediately do solvent extraction in carbon, right? So convert to iodine, do separation. You require antimony, make the hydride, distill it. You require ruthenium, make it ruthenium tetraoxide, distill it. So depending upon the chemical property of that element, you can find out a chemical separation procedures. Rare earths, they form very stable fluorides. Fluoride followed by hydroxides, 2-3 cycles, and you get pure all rare earths in one. So all across the periodic table, depending upon your requirement, you will have radiochemical separations required for these elements. The heavy elements, transactinides, you see here from here, 104, 5, 6. Most of them, the chemistry is not known, and their chemistry with regard to their lighter homologs are studied. How do they compare, like rutherfordium and hafnium? So you can use the lighter homologs as tracers to study the chemistry of heavier elements. So let us discuss some of the radiochemical separation procedures. For example, you do precipitation. Precipitation also can be done in different ways. One is the direct precipitation. You can take just an example. I was discussing rare earths. You want to separate. All of them are trivalent except cerium, which can be present as cerium-4. All others are trivalent. And so this trivalent rare earths can be separated by a cycle of hydroxide followed by fluoride. So fluoride precipitates of rare earths are clear cut. So they are very fine, low volume. Only zirconium may interfere. And so you can do steps of fluoride and hydroxide precipitation. Zirconium will be there all along. So you can do gamma spectrometry, you can separate, or you have to go for some complexing agents. They are called, again, they can complex one metal ion, keep it in the solution form, while others remain in precipitate. So rare earths can be separated fluorides. Strontium barium separations are very, because strontium is pure beta emitter, strontium 90, and barium. So if you want to separate them, you first dissolve, then you first make precipitate as nitrates, then you do ferric hydroxide scavenging to precipitate out the rare earths, zirconium, other things, and then you separate barium and strontium. Barium goes as barium chromate, and strontium will not precipitate as strontium chromate. Similarly, silver can be precipitated as silver iodide, famous your silver chloride, silver iodide. So there are many more examples. I am just taking some of them. Other than this direct precipitation, there are cases like you can adjust the oxidation state of two elements and separate them. For example, cerium and zirconium both are tetravalent and they precipitate as iodate. If you want to separate cerium from zirconium, cerium can be reduced to ceric to cerous by a suitable reducing agent, and then you can separate zirconium as zirconium remains as iodate, cerium comes in the solution. So by playing with the oxidation state, you can do radiochemical separation. One of the very innovative idea is to do isotopic exchange with a pre-formed precipitate. So you don't have to add the precipitating agent afterwards. And this is required when you have a very short-lived isotope. For example, for 138 cesium, very short-lived half-life. So 138 cesium, you want to separate, you don't have much time, maybe within 5 minutes you have to separate. So what you do, not even 5 minutes actually, 1 or 2 minutes. So you can prepare a precipitate of cesium with silicotungstic acid, stable element precipitate, and the solution containing cesium like fission product solution, you just shake it for a few seconds and precipitate. So what will happen? There is a stable cesium in the precipitate of cesium silicotungstate. 138 cesium will exchange isotopically with this one. In a few seconds, you will find most of the cesium 138 has been precipitated with the cesium silicotungstate. So you can just filter this precipitate and you get most of the cesium 138 in the precipitate. So that is called isotopic exchange with the preformed precipitate. Similarly, for technetium, technetium doesn't have any stable isotope. But perchlorate ion and TCO4 ion are quite close in chemistry. So if you have perchlorate precipitate of tetraphenyl arsonium, so this is the precipitate. So instead of technetium, we use perchloric acid and precipitate this out. And again, this precipitate you exchange with technetium. So technetium 99 can be precipitate as a tetraphenyl arsonium perchlorate. So this is like a co-precipitation, and very fast you can do radiochemical separation. Then you have the solvent extraction. It is a very common one. Of you will be knowing that a metal ion, let us say in aqueous phase, and there is a ligand in an organic phase. So when you mix aqueous and organic phases, both liquid phases together, and you shake them rigorously, because there is a potential for the metal ion to complex with ligand which remains in the organic phase, the metal will go to the aqueous phase in the interface, organic phase in the interface, complex with ligand, and the metal ligand complex stays soluble in the organic phase. So you can extract the metal ion from aqueous to organic, and you can then find out what you call as the distribution coefficient of metal ion into organic phase with respect to aqueous phase. The concentration is organic upon concentration in aqueous is called the distribution coefficient. And suppose you are separating two metal ions, they will have their own d value. So the ratio of the d value of A and B is called as the separation factor. So you can find out separation factor for the separation of metal ions in the solvent extraction. Just to give you an example, you want to separate iodine, fission product iodine. Iodine is formed in fission in many oxidation states. So what you do, you first bring all the iodine to I- using thiosulfate as a reducing agent. And now you oxidize I- to I2. So all the iodine using bromine. So now all the iodine is now present in the iodine, molecular iodine, which can be solvent extracted into carbon tetrachloride. So this is how you can do chemical separation by solvent extraction. Similarly, uranium, plutonium, or you can separate them by a reagent called 30% tributyl phosphate in an organic solvent like dodecaine or kerosene. Aqueous phase is 3 molar nitric acid, and they have very high distribution coefficient. All of them will go in the organic phase. So there are many reagents that are used for solvent extraction: to diethyl hexyl phosphoric acid, tributyl phosphate, phenyl trifluoroacetone, tri and octyl phosphate oxide, diethyl ether, methyl isobutyl ketone. And so there are many reagents, which are commonly used to do solvent extraction of metal ions from aqueous to organic. And later on, as a function of different acidity, you can strip them back in aqueous form. So the distribution coefficient depends upon the acidity of the aqueous phase and the concentration in the particular ligand in the organic phase. So you have to play with the acidity to do the separation. Similarly, ion exchange resin. Ion exchangers are very common reagents for separation of different species. So again, it is based on the partitioning of the solute between a stationary phase, that is the resin, and a mobile phase. The mobile phase is the acid, or it can be a base, or it can be a containing complexing agent. So you can have resins based on cation exchange or anion exchange. So like for example, you have a polymeric base styrene or divinyl benzene on which you have the anchored the groups, functional groups like sulfonate, and you have the sulfide group and you have the H plus. So it is the neutral species, but the S plus is exchangeable. So the metal ion in the in the mobile phase can exchange with the H plus and the metal ion will be retained in the resin, H plus will be released. In the case of anion exchange resin, this quaternary ammonium salts containing chloride as a counter ion are exchanging that. So you can have the anions exchanging with chloride, and you have the anion retained in the column, chloride being released. So you can have this ion exchange from different acidic media, HCl, HNO3, HClO4, H2SO4, and so on. But the important thing is that depending upon the ionic potential, metal ions are retained by the resin, and then you can do separation. Just for example, you want to separate thorium from uranium. So you can have an ion exchange resin, DOX 1x8. Keep all uranium thorium in 6 to 8 molar HCl, wherein uranium forms anionic species, but thorium does not form anionic species. So in the anion exchange resin, uranium will be held up, whereas thorium will not be held up. So you can just wash the column, all thorium comes in the effluent, and you can later on elute uranium by using a dilute acid. Similarly, the individual rare earths can be separated using a DOX50 cation exchange resin. You take all of them in 0.1 molar HCl, so dilute acid. So since H plus is not competing, all the rare earths will be held up in the column. And now you want to elute them individually. So there is a beautiful reagent called alpha hydroxy isobutyric acid, which will complex these different rare earths. And since the stability constants are different for different rare earths, you will find because of the rare earth ions having different ionic potential, hence different stability constant. By eluting with this particular reagent, individual rare earths will come one by one. The lowest ionic radius lutetium will come first and lanthanum the last. Another, just similar to ion exchange resin, you have extraction chromatography. So here the ligand actually is on the solid surface. So you have a solid phase, stationary phase, solid phase, some ligand adsorbed onto an inert support that form the column, stationary phase, and mobile phase will contain the metal ions in presence of H plus, OH minus, and so on. So you have a solution containing metal ion and you have a ligand adsorbed onto the solid support. If you pass the solution of metal ion through this column, the metal ion will complex with the ligand and get retained by the column, and later on you can elute that one. Just to give an example of very careful separation of zirconium, hafnium. Zirconium, hafnium are very, chemically very similar because of their similar ionic radii and being in the same group. You can separate them using extraction chromatography. This is one example. The tricaprylyl monomethyl ammonium chloride called aliquot 336 is a extractant adsorbed onto this solid support, and then you first load it from a dilute acid, elute hafnium with 8 molar HCl and zirconium with 2 molar HCl. So you can see here, this I have taken from this paper, that zirconium and hafnium are very well separated. This is hafnium, this is zirconium. So well separated the peaks due to two metal ions in the ion exchange, in this extraction chromatography system. Now, lastly, let us discuss the fast radiochemical separations. Many times you require, the half-lives are very short, seconds, milliseconds, and so on. To even, less than a minute is you require very fast chemistry. And so there are techniques like gas jet transport system. The gas jet transport system, what you do, you have a beam. So you are doing experiment in the accelerator. The beam is going here, you have a target here. Now the target is thin enough, when the beam falls on target, the products are formed in this chamber and the helium gas is passed through this chamber. The helium gas will transport all of them, reaction products, to the fume hood in your laboratory. So you have a pneumatic system and all the reaction products will go in the fume hood. You can collect the gas, the products in a solution, do the chemistry. So the transport time for the reaction products from the reactor or accelerator to the fume hood becomes a few seconds, 1 or 2 seconds. And then the chemistry also, you have very fast chemistry apparatus you can do. Other one is the pneumatic carrier facility. The pneumatic carrier means this is the rabbit. You have a rabbit capsule. This capsule, so target is not in the fixed in the beam, but you have the target is fixed in the, you irradiate the capsule. This is containing the target, like in a reactor, no? So this is the reactor, and neutrons are everywhere. You have a pneumatic tube through which you take the capsule here, irradiate for some time, and later on carry it to the fume hood. So you have to break open the capsule, and the target is present in the capsule. You can separate the reaction product from the target. So here you have only the reaction products in gas jet transport system. You have the target also. So this is a typical pneumatic carrier facility in the Dhruva reactor, what colleagues have built, where you can carry the rabbit in the fume hood into the chemistry. So some of the examples of fast chemistry like antimony, tin, tellurium, you can form hydrides. Within a few seconds, you can separate them. Isotopic exchange with preformed precipitate, solvent extraction. Even you can, in accelerators, for proton beams, you can accelerate, you can radiate in the air. Similarly, for heavy elements, you can do rapid chemistry, automated rapid chemistry apparatus. So you have a gas jet transport system, followed by the high performance liquid chromatography. And one of the elements like, dubnium 105 was separated by this ARCA system using a gas jet system. And you can switch between different columns to do separation of different elements. So atom at a time chemistry means at a time only one atom is formed. So you do thousands of chemistries to do the separation of large number of times, and then that is how you study the chemistry of this element. So thermodynamic quantities of heavy elements are determined by doing chemistry 1,000 times. You have at a time only one atom. And lastly, you have the PET, positron emission tomography. You require short-lived positron emitters like fluorine-18, carbon-11, and so on. So you have to have very fast radiochemical separations because the half-lives are very short. So like, for example, FAT from H2O, you have H2O, you irradiate H2O with the proton beam, and then you separate F18 from this irradiated water using a particular precursor and the catalyst. So this is the reaction given to prepare this F18 FDG. Then you have to have a fast radiochemical separation where within few minutes the whole F18 labeled with the glucose molecule is separated from the irradiated target, that is H2O18. So the whole system is a very compact form, and you can supply the radiochemically pure and sterile sample to the hospitals in a very reasonable frame of time. Maybe few minutes time you can do the separation. So I will stop here. Next I will take the radioanalytical techniques and their applications. Thank you very much.